Greetings and welcome to a series of lectures on precalculus graphs and functions. In this lesson, we will concentrate on the properties of functions. All right, let's talk about properties of functions. We're going to concentrate on three versions of the properties of function. One, if it is an increasing function. Two, if it's a decreasing function. And three, if it is a constant function. Now, let's let f be our function, and x1 and x2 is in the interval of ab. And ab is within the domain of f, so any values between a and b are totally allowable in our function as inputs, and x1 and x2 are any of those two numbers within that group. Now, these a and b could be any values, and it could go as down as negative infinity to positive infinity, but they're just values. They're real numbers. Now, if our x value, our x1 is less than x2, and when we throw them into our function, we get f1 of x1. F of x1 is less than f of x2. Then this is an increasing function. As we increase the value that we input, our function also increases, and therefore this is an increasing function. Now, if x1 is still less than x2, but when you plug them into the function, f of x1 is greater than f of x2. This is a decreasing function. As our x values get larger, our function values get smaller. And if we still have our x1 is less than our x2, and when we plug them into our functions are exactly the same, whether it's at the x1 value or the x2 value, then that is a constant function. So let's take a look at what this means on a graph. It's sometimes easy to see it visually, so let's take a peek. All right, in the first situation, in all of these situations, x1 on the number line is less than x2, and it's within this range of a to b. So a to b is our open interval, and x1 to x2, x1 and x2 are our values we're plugging into the function. So if we plug in x1, it is going to be at the function of f of x1. That's going to be the output right there on the function. And when we input in x2, f of x2 is right here on the function, and you can see it increased from f of x1 to f of x2 along the function. Now let's take that x1 and x2 again, and this time let's do f of x1 right here and f of x2 here. You can see that we went from f of x1 down to f of x2 on the y-axis. That means it's decreasing. So as x gets larger, our f value, our y value, is decreasing. And now we have x1 and x2, and we plug those into the function, and we get out a constant value, f of x1 and f of x2 here, and they are the same value. This is a constant function. Increasing function, decreasing function, constant function. Now, many functions aren't just straight lines. They're very curvy, and sometimes they start low, go high, go low, go high. And these peaks and valleys, or peaks and dips, create what's called relative maximums and relative minimum values. Now, let's consider that we have a value a, and it's in the domain of our function f. We say that this value f of a is a relative minimum if there's an interval containing, well, minimum or maximum. So we're talking about minimum or maximum if these conditions are met. Now, a exists within this interval from x1 to x2. We have to remember that. So a is within this interval. Now, if f of a is greater than or equal to every single f of x, then f of a is a relative maximum. And if f of a is less than or equal to every other f of x, then it's a relative minimum. Right? So if f of a is greater than every other f of x around it, then it's a relative maximum. And if f of a is lower than every other f of x around it, it's a relative maximum. Regardless is if it's a relative minimum or maximum, it's called an extreme value. Now, a lot of words, so let's look at it on a graph. So here I have a graph. I don't have the function for us. I just have a graph with some points. Now, our function goes up and then goes down and up and then down and then up like a roller coaster. Now, every time that we hit a peak, so we have a peak at 1,3, and then we dip down, and then we have another peak at 4,7. These are relative maximums. Every point around it, this one is the tallest one, or this is the highest one. Let's say our interval is from this to this. Okay, just that area right there. You can see that there's a relative maximum. It's not the maximum of everything, but it is a relative maximum for all the values around it. And additionally, if we cut off the rest of the graph, the 4,7 is a relative maximum as well because it is higher than all the rest of the values around it. Now let's take a peek at 2,1 and 6-2. Both of these are relative minimums because again, if I kind of chop off some of the graph, you can see that that is the lowest dip for the surrounding values is 2,1. And then if we do that same idea over here, then 6-2 is also a local dip, and therefore it's a local minimum. Now, of course, 2,1 is not the lowest value of all, but we call it a relative minimum to all the surrounding points around it. All right. Now, when we have these relative max and mins, at that point, it's called a turning point, whether it's at a relative maximum or a relative minimum. These are turning points. Your function was an increasing function until it hit this point and then turned around and became a decreasing function. If you go from an increasing function to a decreasing function, then your turning point is a relative maximum. If you are in a decreasing function and then it turns to an increasing function, then that turning point is a relative minimum. All right, let's look at an example and find our relative maxima and minima. And we're just going to do this visually by finding the dips and peaks, and aka these turning points. So here we have approximating the relative maximum extrema, meaning we want to find the maximum and the relative maximum and the relative minimum. Now I'm going to use a graphing calculator to do this. So I do have a graphing calculator. Let me turn it on. There's a few things that I want to do. So clear, here we go. Here's my calculator. I'll try and bring it up so you can see what I'm doing here. First and foremost, I'm going to plug in this function. So y equals, and I'm going to plug this in. Now here's my little x button saying x variable to the third power minus x squared. All right, so I've got my function in here and I can graph it right now, so I can hit graph, but sometimes it's not enough. I've got to change the window settings to make it fit better. So I'm going to go to my window and I'm going to change my window settings, and I'm going to kind of guess to where I want to see my values. Let's start with just My x minimum is -10. My x maximum is 10. Steps I'm going to do by 2. Minimum is a -10 on the y. Maximum is 10. And I'm going to increment by 2. Now this is just a guess on my behalf on how big my window needs to be. So I'm going to make my x values go from -10 to +10, and I'm going to scale it by 2. I'm going to go from my -10 to my +10 on my y, and again I'm going to scale it by 2. It honestly doesn't matter. We can scale it by 1 and get more of a smooth curve. And I'm going to graph it. And I'm going to take a look. Okay, cool. I can see what my function is doing. But the goal is to try and figure out if there's any peaks and dips. And right now it's a little too small for me to see. So I need to really zoom into this area right around 0. So I'm going to change my window settings. And instead of from -10, I'm going to change that to -1. My x max, I really don't need it to go to 10. I'm going to have it go to 2. I don't know. I'm guessing at this point. I just really want to see around 0. The scale, I'm going to do 0.1. Since my window size only goes from -1 to 2, I can make my scale smaller. And my y minimum, again, I think I'll go -1. And my max, maybe I'll go 2 as well. And again, my scale, 1/10 of the scale. And I'm going to go ahead and graph it. And hopefully, if I've set up my window correctly, I'll be able to see on the calculator where my peaks and valleys are. Much better. Looks like I've zoomed in enough. Now, it's hard to tell on this particular graph where things are. So I'm going to hit the trace button. And when I hit trace, you'll see that there's a little blinking dot on my graph. So first and foremost, I'm going to try and find this little peak right over here. So I'm going to start kind of right here on my graph, and I'm watching my y values. My y values, once they get larger, they're going to reach a maximum, and then they're going to get smaller again. That maximum is what I'm looking for. So right now it's a -0.09, -0.0.07, 0.06, 0.05, 3, 2, 2, 1. It's getting really tight. Okay, I've hit 0. All right, so I was negative right here, and then I hit 0. But now I'm negative again. So 0 is my peak. So 0, 0 is my extrema for my maxima, my relative maxima. Now there's a little dip here. It falls below the x-axis, so I know there's a dip here. And I want to go look to see what value it is. So I'm going to get close to the dip. I'm going to, again, watch my y value. Right now my y value is -0.11, 12, 13, I'm getting lower, 135, 139, 142, 145, 147, 148, 147. So as low as I can go is -0.148 is the lowest that I can go. So my relative minima is going to be -0.6591, and the y is -0.1481. I'm sorry if it's hard to see that. See if it will focus. It might not focus. Focus. There it goes. Okay, so that's my minimum that I can do. All right. Focus back on the paper for you. Beautiful. All right, so that's how I would utilize my calculator to approximate my relative minima and maxima. Graph it and then just find trace and do it again. All right, let's try another problem. Now this problem is from your book. I'm not going to read the whole thing to it, but it has to do with the velocity of a cough. And the velocity of the cough through your windpipe has to do with the size of your windpipe and some other things. So I've grabbed the equation, and I'm going to graph this again. And, or I'm going to graph this and see where our relative minima and maximum are. Now, it looks like a complicated formula, but they are giving us some information. C is going to be 1, so C is 1. R naught, or R0, is 13, so this R0 is 13. And R can be any value from 13 over 2, aka 6.5, all the way up to 13. Cool. Now, I'm going to go ahead and bring out my calculator one more time, and I'm going to change my function. So right now my function is x cubed minus x squared. I don't need that anymore. I am going to need this function with a 1 for the 3 and a 13 for the R0. And I'll leave the R's alone. And because I really don't have an R value, I mean, a variable is a variable. So I'm going to use x in place of R just for my plotting capabilities. I think I might be able to, I don't know, try and figure out another value besides x, but I'm not going to fight the calculator. All right, C is 1 times R naught is 13 minus our variable times our variable squared. That's our formula. But I've got to tell the calculator that I only want it to go from 6.5 to 13. That has to do with my window settings. So I'm going to go back to my window. I'm going to go from 6.5 to 13. And my scale, let's see, 6.5 to 13. We should do it every half a point maybe. My y minimum, since this is velocity, I don't really care about negative velocity, so I'll leave it at -1. And my max, I'm not sure what my max is going to be, but here's the thing. If I plug in a 13 here, 13, and I even put just a 6 here, 13 minus 6 is 7. And this would be 6 squared, so this is really 6 times 6 times 7. That's going to be greater than 300. Well, close to 289 or something like that. And because that's up to 289, I know my max has to be greater than that. So I'm just going to do it, let's see, 400. All right, so my y maximum is going to be like 400. And of course, my y scale isn't going to be 1. I'll do it by 5s because I don't want my screen to be crazy big. So let's just go 5 and see how it graphs. So I'm going to hit graph. And okay, it looks like I have a little peak here, maybe sort of. But I'm going to zoom out just a little bit on my window. I know I'm only interested in 6.5 to 13. So just to get a better handle on what the picture actually looks like, I am going to zoom out a little bit. So I'm going to change my window. Instead of starting at 6.5, I'm going to start at 0. I'll leave the 13 there, but I'll just start at 0, and I'll leave everything else the same, and I'll graph it again. Oh, okay. So now I at least see that definitely there is a peak. I don't really care about anything going on this side because, again, that wasn't in my domain, but I just put it in there so I can graph it nicely. And I need to know what this peak is. So I'm going to hit trace, and I'm going to start to slide across. And I'm going to see if I can get this down a little bit lower so I can have it a little bit bigger for you. And see if it will. There we go. All right. So I'm going to try and figure out how large my largest y is. So as I move over, you can see that it's increasing to 90, 293, 297, 303, 36, 311, 313. Okay, visually I'm getting close to the peak. So I'm watching 321, 22, 23, 24, 24.9, 25, 25.4, 25.3, 25.4. This looks like the peak is when x is 8.6667 and y, the output, would be 325.4815. That's our peak. So we'd throw it into a calculator and let the calculator graph it for us. All right, let's talk about what it's like to be an even or odd function and about symmetry. Now, an even function comes down to this. We have a function, and for every x in the domain, it also has a negative x in the domain. And f of negative x equals f of x. So it doesn't matter if you plug in an x, it will pop out a value. Let's say it's 2. F of x equals 2. F of negative x would also equal that 2 as well. So f of negative x equals x of x. F of x, oh my gosh. Now, the graph of an even function is symmetric around the y-axis. So if that means we have a symmetric around the y, it means I could literally fold this paper in half, and along this line, it looks like a mirror image of one another. So on the left would be a mirror image of what's on the right. All right, so let's see an example of graphing the squaring function. The squaring function is when we take a value and we just square it. So let's not try and make it too difficult. So f of x equals x squared. Now, if this is an even function, then f of x will equal f of negative x. Well, we know what f of x equals. That's x squared. We need to figure out what f of negative x equals. So if f of negative x would equal negative x squared, well, negative x times negative x is positive x squared. And I know x squared equals x squared, and therefore f of x must equal f of negative x. And therefore we have now shown that the squaring function is an even function. Now, to be an odd function, let me show you the picture first. So here is a typical squaring function. And you can see that it's symmetric around the y. It looks like a mirror image on each side. So the squaring function looks like this. And if I was to fold that paper in half, this side of the graph would lay right on top of that graph if I could graph really straight. Should have let my calculator do that, right? All right. Now, what's an odd function? If an even function means that f of x equals f of negative x, well, then an odd function turns out that f of negative x equals negative f of x. Even function, odd function. Even function, odd function. Okay, so if I just remove that little sign, that's the definition of an even function. And if I put that negative right in front, that is an odd function. An odd function is symmetric around the origin. So the origin of a graph. Let's show that the cubing function is an odd function. Well, to be an odd function, I need to show that this function, g of x, when evaluated at negative x, is negative g of x. All right. G of negative x equals negative x cubed. So I'm just throwing in a negative x here, and I get negative x times negative x times negative x, which is negative x cubed. But x cubed is g of x. And therefore, g of negative x equals negative g of x. So I can replace the x cubed with the named function of g of x, and you'll see that g of negative x equals negative g of x. And therefore, we can show that the cubing function is an odd function. Now let's take a picture of what that looks like. The graph of the cubing function looks like this. Swoops up and goes up. So if I have an x value, you plug it in, it's g of x. If I have a negative x value, that's negative g of x. So let's just take a few values and see if this really works. Because if it does, and if I know I have a function that's odd, I only have to do kind of half the graph. And then I'll know what the second half is. Let's try x equals 1. X is 1, and therefore x cubed, which is 1 cubed, is 1. Let's try it down here. Negative 1, well, negative 1 cubed is negative 1. Well, g of x was 1, and that's indeed negative 1. Let's try x equaling 2. X is 2, so x cubed is 8. Negative 2 cubed is negative 8. So you can see there's a correlation. I would really kind of only have to figure out this side of the graph, and then I know it's symmetrical around the origin. So instead of just folding the paper once to fold it in half, I would also have to fold it horizontally as well. So not only in half vertically, but horizontally as well, and then this graph becomes down here. So let's take a look at some examples, and we want to test to see if these are even or odd functions. The first one, g of x equals x cubed minus 4x. F of x is x squared plus 5. H of x equals 2x cubed plus x squared. Let's work through each of these examples. So the first one, g of x equals x cubed minus 4x. Now we really have two choices here. We have, is it an even function? So that means g of x equals g of negative x. Or is it an odd function? G of negative x equals negative g of x. So those are really our only two options. But both make me put a negative x here to actually test it to see if it's odd or even. So let's go ahead and figure out what g of negative x is. That's going to be negative x cubed minus 4 times negative x. Negative x cubed is negative x times negative x times negative x, and negative 4 times negative x is positive 4x. Negative x times negative x times negative x is negative times negative times negative is negative. X times x times x is x cubed. And therefore we have negative x cubed plus 4. Now, because I really want to see if g of negative x either equals g of x or g of negative x equals g negative g of x. This is going to be even situation, and this is going to be odd situation. Right now, this negative x cubed plus 4x is not g of x because we have x cubed minus 4. The negative is opposite of the positive is opposite of the negative. So if I factor out a negative here, I get negative x cubed minus 4. Well, x cubed minus 4 was g of x. And therefore, I know that g of negative x equals negative g of x, and therefore, it must be odd. G of x is an odd function. All right, let's try the next one. F of x equals x squared plus 5. Now, the rules are the same. This time I'm using f's, so either f of x will equal f, and let me write it the way that I did up there. Let me sneak in a little negative right there. And f of x, that would make this an even function, or f of negative x equals negative f of x, and that would be an odd function. So I'm looking to see if I fit into either one of those categories. All right, let's plug in a negative x and see what happens. F of negative x equals negative x squared plus 5. Negative x squared is positive x squared plus 5. And, well, positive x squared plus 5 was indeed our function. So f of negative x equals f of x, and that means it's an even function. Third option. Let's go to the third example. H of x equals 2x cubed plus x squared. Same type of situation. If h of negative x equals h of x, then it's even. If h of negative x equals negative h of x, it is odd. All right, these are the things I'm trying to hit up here. Either way, I've got to plug in the negative x and see what happens. So h of negative x equals 2 times negative x cubed plus negative x squared. Writing this out long way is going to be 2 times negative x, negative x, plus negative x times negative x. Negative times negative is a negative, so that makes it negative 2x cubed. But a negative times a negative is a positive, so that's x squared. Now, generally speaking, I'm looking at the sign in front of the 2 here. I have a positive and I have a negative. Those are opposites. So I'm going to go ahead and factor out this negative from the first term and the second term. So I get negative 2x squared minus x squared. Aha! Now, 2x cubed is fine, but minus x squared does not match up with our original function. And therefore, h of negative x does not equal the negative of hx, and therefore it's not odd. And h of negative x does not equal h of x, does not equal the original thing, and therefore it's neither. It's neither odd or even. It's just neither. All right, last thing we're really going to focus in on is average rate of change of a function. We're going to let us have 2 points. I know this looks very complicated in notation, but this is just 1 point and another point, and these points are on the graph of a function. Then the average rate of change of this function as x changes from this a value to the b value is denoted by the function evaluated at b minus the function evaluated at a all over b minus a. Now, this function evaluated at b and function evaluated at a is the change in the y's. And the b to the a is the change in the x's. And we don't want a to equal b, because if a equaled b, then we had 2 minus 2, and that equals 0. Or 5 minus 5 is 0, and we don't want to 0 down in the denominator. So this change has some value, and it's not, b minus a is not 0. And although this formula looks very complex, it is not, and you have seen it before. It's just written differently. This is in function notation, and let me write it in another way to see if it's familiar to you. If that looks familiar to you, that is the slope formula of a line. And indeed, that's what this really is. It's just in a different notation. This is in function notation, and this is just using the points. y2 minus y1 all over x2 minus x1. That is the same function as above. Now I want to talk about this little symbol. It's a triangle, and it is the Greek letter delta. And delta stands for change. So this is delta, and it means the change in y over the change in x. Same thing with our slope formula. This is the change in y over the change in x. This looks a little bit more complex, and it's one step getting you closer to the fundamental theorem of calculus, which is what we study in calculus. And seeing as this is a pre-calculus class, of course we're going to hit you up a little bit slower when it comes to getting you to that point of function notation and these idea of changes. All right, so let me get rid of that little formula. And this delta is just the change in y and x. All right, now let's take a look at a graph. All right, now our function does not have to be a straight line. In fact, this is quite a curvy line, a curved function. And when we're talking about this average change, we're going to take this one point, a of f of a, and this other point on the function, b f of b, and we're going to find the slope of that line. How do we do that? We figure out the change in x. We went from a to b, so the change here is going to be b minus a. We went from f of a to f of b on our y-axis, so the change here is going to be f of b minus f of a. Now, if it helps you, just think of these as points and you're working on the slope of the line. Let's take an example. Here's our function. F of x equals 2 minus 3x squared as x changes from x1 to, or x equals 1 to x equals 3. All right, first and foremost, we know that x is changing from 1 to 3. So we actually have the bottom portion of our equation. We have to figure out f of 3 and f of 1 because we went from 1 to 3. So a few calculations here. F of 1, wherever we see an x, we're going to plug in this 1 value. 2 minus 3 times 1 squared. 1 squared is 1, so 2 minus 3 times 1. That's 2 minus 3. Keep wanting to put times there for some reason. And we get negative 1. So this f of 1 value is negative 1. Let's do the same idea, but now this time our x value is 3. 2 minus 3 times 3 squared. 3 squared is 9, so we have 2 minus 3 times 9. 3 times 9 is 27, so 2 minus 27 is negative 25. All right, so our formula is f of b all over f of a, or f of b minus f of a all over b minus a. Now when I'm putting in these values, this is really f of 3 minus f of 1, and the bottom is 3 minus 1. So I'm just putting in all the values that I'm given. I'm given x to 1 to 3, so I'm putting in all the values into my formula. Now f of 3 was negative 25 minus f of 1. Well, f of 1 is negative 1, so I have this double negative here, and that's over 3 minus 1. The double negative becomes a positive, so negative 25 plus 1 all over 3 minus 1. Now I'm going to combine some stuff. Negative 25 plus 1 is negative 24. 3 minus 1 is 2. And negative 24 divided by 2 is negative 12. This means on average it will go down 12 on the y for every one step we move to the right. Remember, this is still a slope, it's a fraction. For every 1 unit we go to the right, we go down 12 on average. Now, it's not going to be guaranteed that I would go down 12 everywhere. It's just the average change of a function, not the change everywhere on a function. All right, let's hit up another example for finding the average rate of change of a function. So let's find the average rate of change for the function f of t equals 2t squared minus 3. And t changes from 5 to x. And we don't want x to be 5 because that's boring. We already got 5. So x has to be more than 5. All right, so let's start plugging in our values that we need. We need to calculate f of 5, and we need to calculate f of x. And I'm just going to cover up f of x for now. That we don't see it. And hopefully I can manage to do this together. All right, f of 5. Wherever there's a t, we're going to exchange that for a 5. So 2 times 5 squared minus 3. 5 squared is 25. 2 times 5 is 50. 50 minus 3 is 47. So we know that f of 5 equals 47. Let's do the same process, this time with our second value of x. Wherever we see a t in the function, we're going to plug in an x. F of x equals 2 times x squared minus 3. Well, x squared is x squared, so we get 2x squared minus 3. We know our f of 5. We know our f of x. We know our two bottom values is going to be x minus 5. So let's throw everything in there. F of x minus f of 5 all over x minus 5. These two go together and these two go together. So don't confuse them and flip them around. Make sure your f of x is over your x and your f of 5 is over your 5. F of x is 2x squared minus 3. So to see that better, I'm just going to put a parenthesis right around it. You don't need it, but that whole thing is f of x minus f of 5, which is 47. I'm going to combine like terms in my numerator as best as I can. So I have a minus 3 and a minus 47 is a minus 50. So I have 2x squared minus 50 in my numerator, and I still have x minus 5 in my denominator. Looks like I can factor at least a 2 out for now. So I'm going to factor a 2 out of the first term and a 2 out of the second term. And I get 2 times x squared minus 25 all over 5 minus x minus 5. X squared minus 25. X squared is a perfect square. 25 is a perfect square. So I know I can factor this because I have a subtraction in the middle. That's going to be x minus 5, x plus 5. Aha! So I have 2 times x minus 5 times x plus 5 all over x minus 5. Well, guess what? These two things are exactly the same thing, so I can strike them out. I can cancel them out. And I'm left with 2 times x plus 5. But you can either leave it like that or you can multiply it through, and the average rate of change for our original function of f of t equals 2t squared minus 3 is 2x plus 10. So it's dependent on what our top value of x is, or our top value of t is. So if this top value is 10, then our average rate of change would be 2 times 10 is 20 plus 10 is 30. If our top value of t was 20, then our average change would be 2 times 20 is 40 plus 10 is 50. So this depends on what our top value of t is. Okay, now change doesn't necessarily always have to be positive, so let's talk about the average decrease in sound level. So we have some loudness of music coming from a TV, and if you turn the volume down, that's going to decrease the sound level. So as it turns out, our function about this decreasing sound level from a TV is f of x equals 2500 over x squared. And we want to know the average rate of change when we go from x equals 5 to x equals 10. Now I'm going to plug in 5, figure it out, 10, figure it out, and then we're going to throw it into our formula again. So these are decent calculations or easy calculations, so I'll show them both at one time. F of 10 is going to be 2500 over 10 squared. 10 squared is 100, so 2500 divided by 100 is 25. F of 5 is 2500 divided by 5 squared. 5 squared is 25, so 2500 divided by 25 is 100. Now we have all those parts and pieces. We can move on to throwing it all into the formula. All right. Here we go. F of 10 minus f of 5 all over 10 minus 5. F of 10 we figured out was 25. F of 5 was 100, so we have 25 minus 100 all over, well, 10 minus 5 is 5. Now, 25 minus 100 is negative 75 all over 5. And so our average decrease for every notch we turn down on or up on our TV, the volume goes down negative 15, or I should say it goes down 15, but the value is negative. Yes, it's okay for your AKA slope, your average change, to be negative. It just means that it's decreasing and not increasing. Now, very similar to what we just did is the difference quotient. For a function, the difference quotient is this: f of x plus h minus f of x all over h. And h is not 0. H is a little bit of a change from x. So maybe if x is 4, this might be 4 plus 1, and so that's going to be f of 5. If x is 3, maybe we're adding a half each time, so this is f of 3 and this is f of 3.5, and then your h down here is a half. With that said, we are really getting close to the fundamental theorem of calculus here. This is what you're really going to be looking at when we're talking about the fundamental theorem of calculus. All right, now, equivalently, this is the same thing we've been working with, just f of x minus f of a all over x minus a. This is the same thing where a and x don't equal each other because, of course, in the denominator, we don't want 0. It's a little bit more complex to work with this x plus h in here, but it's not terrible if you take your time. Take your time, slow yourself down, double check your math throughout. You should be okay. Let's evaluate and simplify the difference quotient. All right, here's our function. F of x equals x squared, 2x squared minus 3x plus 5. And we want to find the difference quotient, which is f of x plus h minus f of x all over h. First things first, I know what f of x is. That's this thing right here, 2x squared minus 3x plus 5. So I know this part of the equation. I know what h is. It's just a letter. It's just h. I don't have an actual value for it, but it's just going to stay there. What I don't know is what is f of x plus h. I don't have that component yet. And because I don't have that component, I'm going to have to figure that one out. So wherever I see an x, I'm going to put an x plus h. Right there and right there. All right, here we go. 2 times x plus h squared minus 3 times x plus h plus 5. So all I did was replace all the x's with an x plus h. Next, I'm going to start breaking this out. All I did was rewrite the x plus h twice. I'm going to FOIL out x plus h, x plus h. X times x is x squared. X times h is 8xh. H times x is hx, but it doesn't matter which order I write it in, so I'm going to go ahead and keep it as xh. And h times h is h squared. Now in the next step, I'm going to combine these xh's, and I get 2 of them. So that's the only step extra I did, was I combined those two xh's, and I get the 2xh right here. Now I'm going to distribute the 2 along the first term and distribute the -3 along the second term. I get 2x squared plus 2 times 2xh is 4xh. 2 times h squared is 2h squared. -3 times x is -3x. And -3 times h is -3h plus 5. Can't forget that plus 5. All right. That's pretty much it. There is nothing else I can combine. There are no other x squareds. There's no other xh's to combine. There's no other h squares. There is no other x's, h, or constants. So there is nothing else that, there we go. There is nothing else that I can combine. So that is, sorry about that. That is what f of x plus h actually is. Now I know what f of x is. I know what f of x plus h is. I am ready to start plugging everything in. All right, to simplify this, I'm going to combine everything in my numerator first if I can, and then I'll throw it on top of the denominator of an h. So I'm just working with the numerator stuff. F of x plus h minus f of x. This whole entire thing was f of x plus h, so I just rewrote it, minus the f of x, which is the 2x squared minus 3x minus 5. I need to distribute this negative through each of these terms inside the parentheses. And I get -2x squared plus 3x minus 5. Now I'm looking to get rid of stuff. So I have a 2x squared here minus 2x squared. They go away. -3x and a positive 3x, that goes away. Plus 5, but minus 5, that goes away. The only thing I have left is 4xh plus 2h squared plus or minus 3h. All right. There is my numerator. Now, just to make this a little bit simpler to read, I actually reordered it. I just switched the h squareds to the back. It's just, for me, easier to read it that way. And as it turns out, each of these terms has an h, so I'm going to factor out the h. And I get h times 4x minus 3 plus 2h. Oh, you thought we were done. Nope. We need to now put it all over h. So I have h times 4x minus 3 plus 2h all over h. The h out in front and the h down in the denominator cancel out. Do not cancel out this h. It is connected with some other addition and subtraction, so you can't get rid of this h. It has to be factored out first to be able to cancel it out. And we now know that the difference quotient for our function of f of x equals 2x squared minus 3x plus 5 is 4x minus 3 plus 2h. So if h was 1, then you could plug a 1 in here and figure it out. If h was 2, you could figure it out. If h was 0.5, you could figure it out in terms of more numbers. All right, that is it. I know this was a little bit longer than I wanted, but there was lots to cover. So I hope you stayed in there. I hope you learned lots. Until next time, be seeing you.